All right. So if we can X. All right, we are recording. So we want to look at we established a list of various languages which are decidable. And now we're taking we kind of expanded our terminology to represent acceptance by for example, a CFG is given some grammar and string, determine that G generates string W. So it says, if you give me a CFG and a string, I can tell whether that string can be generated by that CFG. Right? So we said at the beginning, among the things that we said are decidable. Decidable, let's talk about decidable versus undecidable first. Decidable means what? It can be decided. It will accept it or reject, and it will stop. Guaranteed to stop. And so all the things that we've looked at so far logically fall into that category where we modified our symbology a little bit. We say a DFA is acceptance. A DFA saying, given a DFA and a string, I can determine whether that DFA would accept that string or not, right? And the justification for that is pretty straightforward. Just simulate the DFA on a Turing machine, and yes, we can write a we can execute a DFA, and it will eventually stop. This is the way it's designed. And that extends to NFAs, regular expressions. We can find out whether a DFA is empty or not by tracking to see if I can reach the start symbol from the accept states. We can find out whether two DFAs accept the same language or not by doing that series of constructions on symmetric difference. And then we ended up looking at CFGs. Similarly, we can do by putting it into a particular form we did not dwell on, we didn't touch on, Chomsky normal form. We're guaranteed that we can, if the string is in there, it will generate within twice the length of the string minus 1 steps, and 2 times n minus 1 steps. So we can try to generate the string and tell whether that CFG can generate a string or not. So those are all decidable languages. So what about undecidable ones? What are problems that are guaranteed that we cannot decide them? We cannot come up with a solution that's guaranteed to stop on any input. And we're going to look on page 207. I'm going to walk through the undecidability. Basically, we start with the statement, page, going back. Our theorem on page 202 telling whether the formulation for that, just to put it in the same format as this, given a machine and a string, M is a TM and it accepts W, which means, right, for it to accept, it would have to end up going to an accept state at some point in time. So this is the problem of acceptance by a Turing machine. Right? Same format here. Given a CFG and a string, we say that is decidable. Right? This one is decidable. We're saying this one is undecidable. And we're talking, could you ever, you can imagine the degenerate cases, the places where artwork, the places where you have a empty string and a Turing machine that has one state that just goes to the reject state, right? So you can think of the weird edge case or something. Go, well, that would be decidable, right? It's like, well, you can contrive a decidable single instance, right? Does that prove that the language we define here is decidable? No, I mean, you have to, what you'd have to do is, if you're using that method, you would have to try every single instance of every single Turing machine and show that, yes, we can, I can tell whether it accepts this, all these strings, right? So the kind of objection that, well, I can think of a single case that might be decidable is not sufficient proof for you. What we're saying is that the general problem of you give me any Turing machine and any string, and I can run it through my little decider and come up with an answer, yes or no. That's the thing that is not decidable. We're not guaranteed to get an accept or reject. So if something is undecidable, we never know whether it will, or it is not guaranteed to terminate. It's not guaranteed to come up with true accept or reject. And it could run forever, And there's no way that we can tell whether it's running forever or we just haven't waited long enough. So that's where undecidable element comes in. So we want to walk through a proof by contradiction, which comes from assuming that this is decidable, and then coming to a contradiction that says you can't do that. You can't build that. So we start with so here's my he calls it H for halt. Right, so if we can tell if this thing will stop, if we had a way to tell whether it'll stop, we could figure out that it's either going to end in an accept or reject state. So we assume that acceptance by Turing machine is decidable. Okay, so proof by contradiction starts by assuming what you want to prove false, assume that it's true, and then show that logical implications of that lead to a contradiction where that would not be possible. So if it is decidable, let's say we have a decider for ATM. So we propose H of, give me the machine and the string, and I will tell you it will accept if M accepts W and reject if M rejects. That seems reasonable. So this is a decider, right? So if ATM is decidable, it's perfectly logical that there would be a decider. I mean, that's the definition, right, of decidability, is there exists some Turing machine which can decide that language. So now we propose a new Turing machine. Suppose this exists. Now I say, okay, well, I'm going to use that as a subroutine for a new definition. Every time I say Turing machine, we can kind of plug in the word program, right? So the Turing machine is a program that has an algorithm that processes data and will say accept or reject. Our new machine D. Okay, so it's going to take Turing machine and a string, and I'm sorry, we're going to do D of just M. So it can take a Turing machine and it's going to use H on input M, D will run H. And I put the opposite of H's answer. So if H accepts, D rejects. If H rejects, then D accepts. So imagine something like this logic. Let's see. People. So the little caution is it too weird to think of a machine running with its own description as the input? A little weird. But we could do it, right? We could, let's just say, we've got the source code would be a good description of a program, right? Just moving it into what we're more familiar with. You can imagine a Turing machine can be described according to the formal definition that we have in the book, right? Set of states, you can enumerate the states, the transition functions, the list the accept state, the reject state. It would have all the tape movement instructions, everything, right? We could describe that text, we could describe that in whatever format, right? I mean, we can represent it. We know if we can do it in English, we could somehow distill it down into something that would encode it efficiently. Or consider just a Java program. Okay, try to put it into something familiar. If you have a Java program and it can read files, and you can run it, and its input is its own source code. Okay, so I mean that's kind of plausible, right? We can imagine that. You could imagine a little maybe weirder, a compiler written in Java, right? I mean, if you want to think about programs that process other programs, think of a compiler for a language. Say that compiler is written in Java, and it takes as its input its own source written in Java. Okay, so trying to make it like, okay, it's kind of plausible at least, right? So you feed M, a machine, into this new machine called D, which is a decider, right? And you plug that in. If you give it, it just takes one, some description of a machine, then it calls H, and gives as the input to it the same description of the machine. So it's going to says if this machine processes its own description, H will say yep. If it says accept, then H can see that, and if it's going to reject, H can also determine that. So H is going to be a decider, and it's going to stop. It's guaranteed to stop. So now we've set up this scenario, and the question is, what happens when we run D with its own description as the input? I get this weird contradiction thing. It looks a little bit like maybe a little bit like a parlor trick. Wait a minute. I think the rabbit was actually underneath the table, not in the hat. So if I run D on its own description, D is a machine, has its own, it's a think of it as a TM or just a program. We run it on itself. What results will it give? Is that possible? Well, that's the contradiction that we end up with. If you could come up with, our conclusion is it can't do both, right? It can't, it's going to look at its own input, it's going to call it self. You feed it D here, it's going to call H of D, comma D. If H says, yes, this will accept, then D is going to turn around and say, nope, I reject, and vice versa. So if it would reject, it's going to say it accepts, but it can't do that because we're feeding it this, so it's giving the opposite of what it would do. So we conclude neither D nor H can exist. So where does that take us practically? This is called the, or a variant of the halting problem. Has anybody recall hearing of the halting problem? Halting problem says, does somebody have an offering of what your understanding of the halting problem is? Ish. Take a wag at it. One formulation of the halting problem would say if that you, based on the idea that you cannot tell if a machine you cannot decide, ATM is at the heart of it. It says you cannot write a program, right, in the most practical application. You cannot write a program which can take another program as description and some input and decide whether that program will halt on that input. Again, you might think of, that's a little uncomfortable. What we're saying is it's theoretically, it's like impossible. It's something you cannot even begin to do. So our sense of problem solving, I think, and logic kind of says, now wait a minute, does that mean I could never write any program that could tell whether a particular little tiny program would stop or not? It's like, well, and again, if you narrow it down to a specific case, you might imagine, can you write a program that would tell whether a Java program that's only statement is A equals 27 would stop or not? Yeah, if I could maybe even expand that to the only line in the program is in a single assignment statement into a variable of a constant integer. Will that stop? Yeah, I could write a program that would tell that, right? In the essentially you've removed any, as soon as you remove any possibility that the program won't stop, right? I mean, it's a stopping program, then you've kind of taken away the question of whether you could tell whether it stops or not. Does that make sense? So, again, the kind of edge case, the weird, can I come up with a contradiction to this? Does not disprove the statement that there we go, that ATM is actually undecidable, right? So what we're saying, to formulate it generally, if you try to come up with a program that will take any other program and tell whether it will stop or not, that is undecidable. You cannot write a program that will perform that task. You can't tell whether the other, if you, how could you possibly attempt to do such a thing? Well, emulating the program, executing it, right, will, you can, if it stops pretty quickly, you can tell that it stopped. But if it doesn't stop, how will you ever know whether it will stop eventually? And the answer, in the general sense of, can I write a program that will tell whether another program will ever stop on a given input? That is the halting problem. The answer is it is impossible to write such a program based on Turing machine understanding. Say it again, please.
Nothing can exist where there are other loops.
Yes. So reducibility is, I'll give some examples to take it out of kind of completely theoretical realm. So let's start, before we do the totally theoretical side, let's look at some problem that is so there. Okay, so first let's talk about, we will revisit this concept again later, but where does he use? I was going to say transformation. Program. So it's like, oh, B also. So let's take a simple example, hopefully somewhat reasonable, obvious. The idea is we're trying to, a reduction, something like this, we have inputs to program B, and we send, basically we treat programs A as a subroutine or a this. We run our program A, and it comes out with some results, and then we feed those maybe with an X, some transformation get the results out. So let's give a very concrete example. Suppose you want to find the median of, some of you will appreciate this from algorithms. Suppose you want to find the median of a set of data. What is the median, just for definitional purposes?
The middle number.
The middle of the sorted set of numbers, right? So if you have the numbers in ascending order, if you have n numbers, the median would be the n over 2 largest value in the set. Well, if you didn't take algorithms, you won't know about the tricky way to find the median. But what would be a brute force way to find the median? What's kind of the obvious? Here's a pile of data. What do you do to it to get the median out?
Just sort it first.
Sort it, and then you know how many elements there are. You go to the n over 2 slot, and there's the median, right? So program A is quicksort. Program B is find the median. Can we come up with a reduction that will reduce program B into program A, find the results of program A, and then do something to get our correct answer? Right, so quicksort does not in itself find the median for you. Quicksort just sorts the values. So we could imagine,
Although it can accidentally.
as a byproduct, right? One could say that quicksort. It seems almost philosophical argument here. Does quicksort find the median? You have to do a little bit of work to get the median back out, right? So to get the median, we would, if our input is an array A, well, we can just feed that directly in to our quicksort and get back array A. And then what can we do here? My transformation is output A sub n over 2, right? So I have to do a little transformation on the array, a little bit of work. But essentially, I would say that this problem B can be reduced to quicksort, because by running quicksort on my data and getting the result from there, I've essentially solved my median problem. So, I guess in words, B can be reduced to a known. The idea is we have a problem that we need the solution to, and we reduce it to a known solution that we can then use that result with some possible transformation, additional work. And we'd say that B can be reduced from A. Right, so we're going to use that idea here. Reduce. Now we're going to. Now we're going to use this concept to do some further proofs about what we concluded from the undecidability of ATM, right? So this is what a reduction is, and what our arguments are going to be is, I know that ATM cannot exist. Okay, we've proven that there's not a decider for acceptance by a Turing machine. So if we basically say if I had if ATM is reducible to this problem, or this problem is reducible to ATM, then it is also undecidable. So you kind of say, well, wait a minute. And one obvious argument would be, let's say problem B could be transformed so that it would solve ATM. Well, ATM can't exist, so the fact that you could reduce this problem to ATM means that neither can it exist. Or if some problem B would solve ATM for you, it cannot exist either. So ATM is going to be kind of our workhorse, what we try to find reductions between. So let's see, he gives, I wanted to, a couple of things. Reducibility always involves two problems, which we call A and B. And I think I lettered them slightly backwards from his A and B, but in his wording, if A reduces to B, then we can use the solution to B to solve A, or the other way around. So in our example, if A is the problem of finding your way around the city, B is the problem of obtaining a map, reducibility says nothing about solving A or B alone, but only about the solvability of A in the presence of a solution to B. So if you had the existence of, he's taking it to keeping it in the kind of theoretical realm. We do actually come across reductions where, yeah, if we know how to solve one part, right? I mean, you probably have done this before if you've ever pulled out code that solved a problem that you had to deal with previously, and you had to refactor it, or I'm assuming, right, you're not just rewriting an entire, not just saving the variable names, but if you're saving this essence of the algorithm and going, oh, wait a minute, I can just do this with it, then you've done a reduction essentially to an existing solution. So we know that we can't tell ATM is not decidable. What about, this is the definition of the halting problem, putting it into terms specific to whether any Turing machine will stop on a given input. So I'm over on page 216 if you're tracking along. And we're looking at not acceptance, but halt TM that says, whoops, if we are given a machine and input, this will decide determine that given this machine and this string, M halts, stops. Okay. What would be a reduction? Basically, we assume that a Turing machine R decides the halting problem. See if we can get their logic here. We start with, we construct, let's assume that R okay, so we say, okay, again, we'll assume that marker is reaching its end. So we are going to construct a new Turing machine S. New TM called S. It does the following. Oh, S M W. We run this little guy, the halting thing. So if from this on here it says, this is answering the question, will M stop on input W? So accept means yes, it will stop. Reject means no, it will not stop. if so if R says nope, this thing's not gonna stop, then reject. They kind of did it. No, we're good. Simulate the execution of M on W until it stops. We know it'll stop. And then basically what we're doing here, you can see through the veil. So if M accepts, we accept. And if M rejects W, or ends with reject on input W, then we reject. What do we do? If this exists, then what we've done is reduced what the acceptance by TM. This decides, or S ends up deciding the TM. So if you had this guy, then you could solve ATM. Yes, what are we doing? The problem with ATM is it's that never stopping element, right? So if you had something that could tell if it would stop, which is R, halts, if M halts on W, or accepts if M halts on W and rejects if M won't stop. Well, right here is where this is stopping is here. Right, that little thing right there is the whole problem with why you can't just simulate the Turing machine on W and get the result, right? Because it might accept, it might reject, or it might run forever. So if you take out the run forever, you solve ATM. And so what did we do? We reduced the halting, acceptance by a Turing machine. We reduced it, means we used R to get a solution to lead us to results. So the halting problem can be reduced to finding out whether the thing is going to stop or not. Therefore, what do we conclude? Since this cannot exist, this, which would solve that, also cannot exist. So that's how we conclude that halting problem, halt of TM, is cannot exist. So that means it's undecidable. Go on to do something similar with detecting whether the language of whether the language of the Turing machine is the empty set. In other words, it always rejects. That even is undecidable through similar kind of proof. And what about is the language of a Turing machine regular or not? Well, if we know that the Turing machine emulates a DFA, then yes, we could tell that if it truly is a direct implementation of a DFA, then we would say yes, it is regular. But in the general sense, there could be many different ways to build a Turing machine that could accept a regular language, or it might not. Our bottom line is to again show that we can solve the acceptance by TM if any one of these exists. Deciding whether two DFAs are equivalent, have the same language, accept the same language, that is decidable. But deciding whether the language of two Turing machines are equal is again undecidable. If R decides two TMs, you feed Turing machine 1 or M and M1 in. We run R to check the equivalence. Well, we make our second machine reject everything, and if the two are equivalent, then we've solved the equivalence problem. But back to finding whether one is empty is undecidable. And so we kind of cascade these down one after another to end up with all the things that are not decidable. I think we'll stop there for today. Yeah, and we'll we are about we're not going to go through all of chapter 5. We're just about done with chapter 5 here, and not going to address chapter 6. So our next topic might have a couple things to finish off in 5, and then we will leap over to 7. All right, see you guys next time.